Well, thank you so much, and thank you for inviting me here. So we're a small group, so let's keep this pretty informal, I think. So stop me at any time. I have a bunch of slides, but I can skip certain things and focus on certain other things. So let's keep this like interactive as much as possible. All right, of course, we are here to talk about automobiles, about which I know very little, but I'm learning more and more, and I'm here to learn even more. And this is a slide that yeah. All right, so this is the usual thing where you say if you treated your car like a piece of software, which we are increasingly doing this, then this is kind of what it will look like with all these patches. So we don't have a great record of building secure software, so why should we think that we can build secure software for cars? It's entirely unclear. But of course, for many of these problems, we often think of cryptography as a solution, and it is, right? So there are secure software updates that we want to have for a variety of devices, including automobiles. There's all kinds of communication protocols which essentially require secure channels between devices, which again we can use crypto for. And then there are very automotive specific protocols for secure charging, keyless entry, and so on, which also, if you look hard at them, are essentially cryptographic protocols that provide mutual authentication. And many of these protocols are standardized. Many of them are proprietary. And they actually form the core of the trusted computing base for automotive software. I mean, at least they should, right? And of course, one of the key challenges, as you guys all know, is that a lot of these mechanisms and protocols and algorithms have to be really long-lived because automobiles are long-lived. And so we have to think about what we are going to deploy well before we actually deploy them. And the cost of having a design flaw or an implementation bug is actually very high. It can be a whole recall in certain cases in components that are not easy to update. And cryptographic components tend to be hard to update because they are actually the trusted computing base. And the point of this workshop, of course, and the point of my talk is that when we are entering this post-quantum transition, it's a time of great churn. We're trying to standardize new algorithms, new protocols, implement them, get them all in now. It is a real churn moment. And a churn moment like this is a moment of great danger because things can easily go wrong. And I'll show you some examples of how they've gone wrong in the past. And on the positive side, it's also a great opportunity because when we are changing so many things, maybe we can do them better this time around. And that's kind of the point of my talk, which is to do high assurance implementations and high assurance protocols this time. So the one message from this whole talk is that if you use formal methods, we believe it can actually speed the development and clarify the security for these new mechanisms, new protocols that we are all seeking to implement, deploy, standardize, and so on. And what do we mean by formal methods? Well, essentially, this is one definition of it. It's applying formal machine-checkable approaches to the design, analysis, and implementation of cryptography. It's sometimes called computer-aided cryptography. And this is basically the idea that when you do a new cryptographic design, you analyze it formally to find attacks or uncover assumptions. Later on, once you're standardizing it, you comprehensively analyze the standard and specification before you publish it and actually do a proof that it's actually secure. And finally, even when you build the implementation, you try to verify the implementation is matching your security goals and the standard specification that you have. And you keep repeating these steps. And you want to do these steps not just once for one artifact, but as the thing evolves, and things evolve all the time, you can keep repeating these steps. And that's the value of having machine-checkable tools and machine-checkable analyses, because once you have done them, you can just keep running them over and over again, even as part of a continuous integration server for your code, or as part of every revision of a standard as you're going through. Okay, why should we do this, or why should we care? Well, here's a historical example. That it's the protocol called transport layer security. That's what is running underneath web browsers. It's usually thought of as a web protocol, but of course, it's used everywhere. Whenever you need a secure channel, the first option you use is usually transport layer security. And then you think about other options if, for example, you have special constraints that do not make TLS a practical choice. And if you look inside TLS, what is it? It's basically a secure channel across an insecure network. And it has some very strong security assumptions and very strong threat models. So typically, if you're thinking in the web scenario, you are on a web tab. I have opened a tab to my bank. All the other tabs that I have in parallel could be to completely crappy websites who are trying to attack me, right? It could be like whatever. I might be pirating movies or whatever. And I'm going through a potentially insecure Wi-Fi network, like here, all the way through to some data center somewhere where my bank has its website. But on that same data center, there might be any number of other websites, including the people who are trying to attack me on my other tabs. Right? So there's sort of bad guys in the data center, bad guys in the other tabs, bad guys on the network. But still, I want to have a secure channel from my tab, which has my bank website loaded, all the way to the banking server, which is also in the data center. And that secure channel I want. And you'll see this pattern repeats itself over and over again in all of the applications we have. Inside a automotive device, inside a car, we want to have connections between different devices. We want to have vehicle to external communications. All these places, we want basically a secure channel across an insecure network. Some cases, we have some stronger assumptions about where the attackers are. Some cases, in fact, there are even more attackers than there are on this page. But this is a very classic problem, very well understood. Lots and lots of models, lots and lots of protocols. And indeed, if you look inside, if you click on the lock inside your browser and you see what is running, it's basically say, this page uses HTTPS. Inside it, it uses TLS 1.2. TLS 1.2 is secured using ECDHA, RSA, P256, blah, blah, blah. Okay? So you can basically break it down and say, these are the cryptographic algorithms that are being used. This is the constructions that those algorithms are part of. This is the protocol that is being used, and that kind of is the application, let's say, so higher level protocol. And of course, the moment you see this, you see, none of this is post-quantum secure. Okay? Now, this because my bank doesn't support post-quantum cipher suits, but today, if you actually connect using Chrome to any Cloudflare website, probably it's going to use a hybrid post-quantum cipher suit. But the protocol that's happening there is very classic. It was designed in 1994. Okay, and then there just kind of had some revisions since. But since 1994, more or less, it looks like this. Okay, it's like a key exchange protocol using Diffie-Hellman. Okay, there is another mode for it. There's 3 other modes, but let's say that's kind of the classic protocol. Well understood. Okay, 2 components: authenticated key exchange, authenticated encryption. The same kind of style is used in SSH, IPsec, TLSs. Many differences and details about how they actually work, but at a high level, it's very well understood. And so it should be a solved problem. It's like 1994, it was already deployed, right? But if you think about it, look at just the period of time between 2011 and 2016, and this is an important time, I'll tell you why. You can see that there was a whole bunch of attacks. Each attack had its own website, it appeared in newspapers, it had a logo, and people would be talking about it. And then all the web servers would upgrade their TLS, all the web browsers would upgrade their TLS to avoid those attacks. Okay, there's a long sequence of attacks. And I don't want to go into all of them, but you can actually kind of pick at them and say, well, what went wrong? What are these attacks about? Where are they coming from? And this is important because we are going through another churn now with the post-quantum transition. Let's try to understand what happened before. If you dig through those attacks, there's kind of 3 categories of things that go wrong. The first is that there are weaknesses in the crypto itself. So there was an algorithm, say MD5, which was considered pretty secure up to 2000, and it was considered very insecure by 2016. So there is a period of 10 years or 15 years where something can go from the default, the fastest, the best way to do something to don't use it. Okay? And this time frame is not as wide as one might have thought in the past. Okay? And this is something that we should keep in mind. The second thing that goes wrong often is that the protocol itself has flaws in it. The design has flaws in it. What kind of flaws? Well, one kind is, which has plagued protocols like this for a long time, is separation. So the separating keys, separating transcripts, making sure that this element in the protocol here does not somehow match the same format as this element in the protocol far away from it. So that happens often when you have 2 or 3 different modes of the protocol. And downgrade attacks. So you have version 1 of the protocol, then somebody puts up version 2 of the protocol, and now there's an attack because version 2 of the protocol can be used to attack version 1 or vice versa. Okay? And again, it's an important question when we are doing this kind of transition like we're going to do now with post-quantum. And the third kind of attack, obviously is because of implementation bugs. Now, we can never get away from implementation bugs. There's always going to be implementation bugs. But the point is, an implementation bug sometimes can really kind of completely bypass the security of a protocol implementation. And it's not just like, oh, it crashed. It's actually like it revealed all my keys. So it can be really bad. And often, in some of those attacks we saw in the previous page, what was interesting was that there was a crypto weakness, but maybe it was hidden because the protocol somehow protected against it, or the implementation did not allow it to happen. Or there was a protocol design flaw, but it only occurred if the implementation did something weird. Or there was an implementation bug, but in fact, it couldn't be exploited. But sometimes you can have all three of these things interacting in interesting ways, causing catastrophic failure. So what can we learn from that, all of that? Well, one lesson is that all crypto, whatever crypto you're putting in there, you have to assume will be broken at some point. Now, the question is when? We don't know often. Let's say 10 years, but it will be no longer usable after 10, maybe 15 years, maybe 20 years. The level of brokenness we can argue about, okay? How strong does the adversary have to be to break it, okay? But MD5 went from something that only governments could break to something that your laptop can break in like 15 seconds very quickly. So attacks get better very, very fast. So the first attack to the really practical attack, it's like a matter of years, okay? So a small number of years. What this means is that whenever you're trying to put in a cryptographic mechanism, if possible, try to make it agile, because you don't know whether the algorithm you're putting in today is going to last. If you can change it, wonderful. Some places you can't change it. If it's like secure boot, it might be very hard for you to change the protocol in that, because it's sort of really the first thing that is happening. So when you're talking about post-quantum, maybe try to do defense in depth. So we really recommend people use hybrid schemes wherever possible. The NSA doesn't like it, but whatever, so that if one thing doesn't work, the other thing will work. The second lesson I would say is that, and this is what the IETF learned from TLS, is that let's try to formally analyze protocols. Pen and paper proofs, formal methods, whatever, formally analyze every protocol before it's deployed, okay? And this has now become de facto standard at the IETF, but even companies like Apple, Signal, Microsoft, all of them, before deploying a new protocol, even if it's a proprietary protocol, they do formal proofs now, because they don't know whether they will be breaking the old protocol that they had, whether the old protocol will break the new protocol that they had. It's complicated enough that we all want to have formal proofs. And especially when you have multi-version protocols. And the third one, of course, we all know this, but it's worth repeating. Implementation bugs are going to kill all your security. So if you do spend all your budget on designing amazing protocols, but your implementation is going to screw you over, you're in trouble. Okay? So what the TLS working group learned from this was when they did TLS 1.3, and that's why the period of 2011 to 2016 was important, when they were standardizing TLS 1.3, which got standardized in 2018, they decided, okay, this time, even before we press the button to publish the RFC, we want to have many, many, many proofs. So you can see between draft 5 and draft 21, there were so many papers analyzing the protocol on drafts of the standard before it was published. And I think this should be the this is how people should be doing even protocols in the automotive sector and in any other sector, any other security critical domain. And some of these were using machine check proofs, the ones in green, and some of them actually found attacks, the one in red. So these were actually useful analysis, not just like check marking, yes, this is good, check this is good, but actually finding problems that were then fixed, right? Which would have been much worse to do after TLS 1.3 had been deployed. Having said all that, TLS 1.3 is something that is deployed on web browsers and web servers. It's very easy to upgrade, right? It takes 1 week for OpenSSL to push a new version, a couple of months for people to kind of just upgrade. In constrained system, embedded systems, in automotive sector, upgrade cycles are much harder. So we have to get this really, really right. So the pressure is even higher. So what are the lessons that the IETF and the protocol community took from TLS 1.3? Well, the first one is that when you're designing protocols and implementing them, collaborating with researchers actively during the design process is very valuable. You can get both positive and negative results very early. And now, in fact, at the IETF, many working groups pretty much require that if you want to get a protocol through the IETF, and it's a new cryptographic protocol, you had better have a formal proof, some formal proof. Without that, they will not accept it anymore. And this is also the case for industrial protocols more and more. So let's now move to the post-quantum world, right? So how does this impact when we do post-quantum transitions, right? So of course, post-quantum transitions a big thing. People are doing this all over the place. I've been personally involved in the post-quantum transition of the signal messenger, so I'm going to tell you a little bit about this. Hopefully, even though it's a very different kind of protocol, it'll give you a sense of what comes up, okay, in real-world protocols. So the details are not so important, but some of you may already know this. This is the classical signal protocol. It has two parts to it. One of them is called X3DH. It does 4 Diffie-Hellmans. Actually, I don't know why it's X3, it's actually X4, but it does 4 Diffie-Hellmans in the very beginning of whenever you start a signal conversation with somebody else. I'm assuming everybody knows the signal messenger. It's the same protocol which is also used in WhatsApp and Facebook and so on. So you've been using this protocol even if you don't know it, right? So the moment you send your first message to somebody you've never talked to before, this is the protocol that happens that establishes the key. And when you start sending messages back and forth, every time you send a message, it runs this protocol, which is called the double ratchet. But if you just even close your eyes and just squint, you'll see there's DH, 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 DH everywhere. And DH stands for Diffie-Hellman, which is the classical protocol crypto construction, which is completely broken by quantum adversaries. So that's known that this is it has very strong properties against classical adversaries. It has mutual authentication, post-compromise security, forward security, all of these things. Quantum adversaries, everything's broken. So they decided a couple of years ago, 2023, let's make this post-quantum secure. And let's try to do the minimal change because it's such a well-loved protocol signal that you don't want to completely redesign it. Let's do the minimal incremental change to this to make it work. So to do that, what they did, they kept the X3DH thing. So all of these Diffie-Hellmans, they kept them. And they added one post-quantum chem, okay? So they added a new secret, which would be produced by a post-quantum chem. And anyway, they were mixing the results of all of those Diffie-Hellmans. So DH1, DH2, DH3, DH4 was getting all mixed together to get the signal key. And they said, well, we are mixing all of these ones. We'll just add the post-quantum secret at the end. So this is just a minimal extension of signal to add post-quantum, right? And I think these are very valuable designs. I mean, these are very useful designs, even for any protocol that you can think of, including IPsec, including SSH, including TLS, including your favorite little baby protocol. If there is a place where you can shove in a shared secret, you can do something like this, Do a post-quantum chem, get a shared secret, and shove in the shared secret into the existing protocol. It's like the least thing that you can do to post-quantumify your protocol. All right, so the idea is very simple. So they just change the protocol in a couple of small places. The rest of the protocol remains the same. And the goal is, well, it's a very small addition. The previous protocol has been comprehensively analyzed by there are many, many papers in crypto, Eurocrypt, all of these places, analyzing the original signal protocol. So let's make sure that the new protocol is also secure. So the first goal, of course, for Signal was, we don't know if quantum adversaries actually exist. We'd better make sure that the new protocol is secure against classical adversaries. And that's a very important lesson. You want to check classical security first because, you don't want your new protocol to be less secure than your old protocol. And once that's done, then the second goal was to ask, is it secure against store now decrypt later, harvest now decrypt later, whatever, passive quantum adversaries who are storing all the signal messages sent between whistleblowers and journalists today, and 5 years from now, 10 years from now, when they have a quantum computer, they will be able to undo them and see which whistleblower actually sent this message and then arrest them or whatever. Right? So that's the kind of threat model that Signal works with. For different applications, you can imagine other threat models. So these are the two questions, right? So how do you do that? So when this first version of the PQXDH protocol was published, I and my colleagues, we decided, hey, we should analyze this. We love Signal, we should analyze this. So we used this methodology. What we did was we took the protocol spec, which is written in quite nice technical English, and we formalized it So we have to define a compromise model. What keys can be compromised? What are the security goals? What are the cryptographic assumptions? What does a protocol do? So we kind of formalize this. And once you formalize this, you can then start checking whether it's secure using a variety of tools. So we use a tool called ProVerif to automatically check if there are some attacks in the symbolic model of cryptography, which is a very abstract notion, a model of cryptography. And every time you find an attack, it might be because the protocol itself was buggy, or maybe you made a mistake in your modeling of it. Either way, you might have to go and fix the protocol spec or the protocol model and rerun it. Once you're not finding any attacks, then you want to do a proof. So for which we use a different tool called CryptoVerif, which uses the same model, but now is actually doing a game-based security proof that the protocol is actually secure. Now the proof may fail, which may be because, maybe you didn't make a strong enough assumption about the cryptography. You assume that it was okay to have an INCPA encryption, but actually you needed an INCCA encryption, which is a very important distinction because it means that you can use this algorithm, but you can't use that algorithm. So once you kind of strengthen your assumptions enough and you can do your proof, now you have a proof that the protocol is actually secure. Both these phases can find problems, like real problems in the protocol. So this is just an example of what the ProVerif looks like. You press the button and it kind of tries to give you attacks saying, hey, this property that you tried to prove there, which is that this is for forward secure, is actually not secure. I'm just showing you a little glimpse of it for you. It's for this purpose, it's not important. We can come back to it if you want. And this is what a proof in CryptoVerif looks like. It's a sequence of game transformations that you do on the protocol until you achieve a protocol which is obviously secure. And you can say, okay, all my properties now hold. Again, I'm just flashing these slides. I'll try to make them available to you on my website so you can stare at them later if you want. And then, of course, you want to check whether this protocol is secure against a quantum adversary. And the ProVerif model, what this means is that we have this quantum apocalypse event, after which all the Diffie-Hellmans and all the signatures are considered to be broken. And we still ask, are the security properties still true? Now, if you were only using Diffie-Hellman in the protocol, which means that all the constructions are broken and the properties will fail. But if you're using Diffie-Hellman and some post-quantum chem, the Diffie-Hellmans will all break, but the post-quantum chem will still give you security, so you should be still able to prove at least some security properties. In CryptoVerif, there is a completely different way of modeling passive quantum adversaries. There's a whole paper about it. It's very interesting. But you can actually model them and analyze whether the protocol is secure against quantum adversaries as well. So what happens when you press the button and ask ProVerif is this secure? So in version 1 of PQXDH, ProVerif said, oop, there is an attack. We said, what is this attack? And it's an interesting one. So what's happening here is that when you start a signal conversation with somebody, what you do actually is, because I want to talk to Bob, and I say, okay, I need Bob's public key, right? How do I get Bob's public key? I ask the signal server, hey, can you give me Bob's public key? Now it's a bit more complicated than that. At least in WhatsApp, it's basically you just click on the UI and it'll retrieve the public key of the recipient. In fact, not just the public key, it'll retrieve a whole key package, which is the public key of Bob, also something called the signed pre-key of Bob, which is signed using the signing key of Bob, and a one-time pre-key for Bob, which is not signed by anybody. It's just a kind of ephemeral key that's there. So there is a signed Diffie-Hellman key that I get for Bob. So for PQXDH, I also need the post-quantum key for Bob. So I also get the signed post-quantum public key for Bob, also signed using the private key of Bob. So there are this Diffie-Hellman key and this post-quantum key, both which are signed by the private key of Bob. So the attack that ProVerif says it finds is that, what I can do is when you ask me for the public key of Bob, public keys of Bob, I will just swap these two. I'll give you the post-quantum key where the Diffie-Hellman key is and the Diffie-Hellman key with the public keys. This is just a signal server. It's untrusted, right? It can give you any key. That's why we have signatures, because it's trying to protect against tampering. So if I flip them, what's going to happen? When you try to do the Diffie-Hellman, you're going to do it actually with a post-quantum public key. All bets are off. It's not necessarily in the elliptic curve group. We don't know what's going to happen. Pretty much it can be insecure. Similarly, when you're doing the post-quantum chem, doing it with a Diffie-Hellman public key, which again is completely insecure. We don't know what's going to happen, what the security of this is. In fact, in certain cases, we know it's insecure. Okay? And if you do this, what is also interesting is that now, because you have introduced this into the protocol, this key can break the original X3DH protocol of signal. So PQXDH can break X3DH. And of course, X3DH can break PQXDH. And within PQXDH, you can also do this game within the protocol itself. So it's not just a problem in PQXDH, it's also a problem in if you have like one device which has not upgraded to PQXDH in signal, it's still doing the old stuff. One device which is doing the new stuff, both belonging to the same user. Now there are all kinds of attacks that are possible. So the upgrade or the transition is completely broken here. In practice, this is not a really practical attack. Why? Because the post-quantum keys we know are 1 kilobyte long, and the Diffie-Hellman keys we know are 32 bytes long. So it's very unlikely that an implementation is going to really confuse the two. It's going to crash someplace and say, oh, I expected 32 bytes, you gave me too big a key, or vice versa. Okay, so in practice, it's not going to happen. Okay, but in the model, it totally can happen. Okay? And you can imagine a certain buggy implementation where that actually can happen. So that's one interesting attack. It's actually an instance of a very classical cross protocol or downgrade or upgrade attack, whatever you might want to call it. And this will happen anytime you do a post-quantum transition for any protocol, right? This is something you always have to be careful about. Is the new post-quantum mechanism going to be, can it be used to attack the old pre-quantum mechanism and vice versa? And are there any new things that you're adding to it? Even if you say, I only added something, but only adding something can break security as well. Okay? There's a more interesting attack, which is more cryptographically interesting attack, which you can find only when you do the crypto proof. And in this case, it's called the chem re-encapsulation vulnerability. And that's because what happens here is that A is sending a post-quantum chem encrypted message to B, and B can re-encapsulate that message to C in a way that A and C get confused about what's actually happening in the protocol. Okay, again, it's a fairly technical vulnerability. It only appears when you do the crypto proof. And this basically shows you that you need a particular kind of binding property in your post-quantum chem, which now people have accepted, and a lot of people are now designing post-quantum chems with various kinds of binding properties. It's become a whole subject of research. This was perhaps the first example of it being found in the wild in a real-world protocol of the problem that now people consider important for the design of these. So sometimes some of these attacks you find could be a protocol issue and can be fixed in the protocol, and we fixed this in the protocol. Sometimes it shows you that the assumption you're making of the underlying crypto is not actually is too strong. And so now you have to go back to the standards body and say, hey, your algorithm that you standardized there has to have a stronger property. And that's what people are doing now with various hybridization schemes for post-quantum chems. All right, and that was just the starting protocol. Since then, Signal has also standardized its post-quantum version of the double ratchet. Again, something that we helped them design and analyze. And what's interesting there is that it's a completely new protocol, and it has lots of constraints, because when you're ratcheting, every message is going to do some post-quantum stuff. And it's too much. If you put a 1 kilobyte post-quantum key in every message, Signal is just going to die. So they found a very clever way of chunking the post-quantum bits into smaller messages so that they can still do it alongside their messaging protocol. Now again, messaging is a very particular domain, may feel very far from the kinds of protocols we're interested in, but the moment you start putting this kind of constraints, like what is the message size, how am I going to do post-quantum in these 32-byte chunks, it starts seeming familiar to a lot of other protocols that we are interested in. What's interesting about this process is that they also did a formally verified protocol design from the very beginning. In fact, they analyzed dozens of variations of the protocol before they settled on the final one. So what we did there in the previous case, they did all the time. And the verification, the protocol code that they developed for this was also formally verified, so that they could keep finding bugs as they were developing it. And I think that gives us some lessons, this whole exercise. The first one is that you can often use standard crypto like MLChem, MLDSA, HQC, whatever standard post-quantum crypto for your transition protocols, but you might want to be open to the idea that even the standard crypto might need new APIs, because otherwise, if you're always going to send big chunks of kilobytes of data, it just is not going to work. So how do you design new APIs that allow you to use standard crypto in a way that satisfies your constraints? This gives you a good example of it, but actually I think for every protocol that this issue will come up. The second thing, of course, is that it was very valuable for them to analyze protocols as early as possible to find bugs early as possible. And once you build the software verification into the code from the beginning, protocol engineers can just run it all the time. So they've been finding bugs in their code whenever they change it, and then they it just becomes part of their daily workload. It doesn't have to be a special thing. All right, where am I doing for time? I'm okay? All right. All right, so that brings me to sort of my goal for this community in some sense. And this is something that we've been working on with Ferris Systems, various other companies, and research groups. And the idea is to build a high assurance cryptographic stack that can be pretty much used by a wide variety of automotive applications, and to do this in a way which is almost exemplary. And the three components here is that we want to use formally verified cryptographic libraries. So the libraries that we want to use for crypto should be formally verified. It's like the base. Without that, we never know what we're doing. The protocols that you are going to use on top should be provably secure, whether they're using pen and paper proofs or machine check proof, doesn't matter. You need provably secure protocols there. And then the implementations that you're using on top of them, which is the protocol implementation, should also be high assurance implementations, which means you should be able to check them for compliance, for various kinds of properties with automated tools, okay? And this, I think, will give us the right kind of pretty high confidence supply chain where basically this stack at least is fully secure. Anybody can check it. It's third parties can verify it. So we can be confident that this is actually doing what it does. And on top of this, now we can build all the other applications with signatures, with secure updates, with all of these things using the stack. Let me kind of expand on that vision in a couple of ways. The first one is, well, what do I mean by formally verified crypto? So there's a whole bunch of crypto libraries that people use, right? I mean, you can use embedded crypto libraries like ARM Embed or PQM4. You can use kind of big crypto libraries like Boring SSL, OpenSSL, NSS, and so on to do which will provide you all the crypto algorithms that you need. But in fact, there's a whole new world of formally verified crypto libraries that are out there, and they are being used by all the big companies now, okay? So there's assembly crypto libraries, which are being used in OpenSSL, other ones from cutting edge research, which is kind of really high speed assembly, which is formally verified. There is code in C, which is in NSS and in Boring SSL. There is code in ARM assembly, which is being used by AWS. There's code in Rust that is being used by Microsoft, but all of these are formally verified to be correct. And what does that mean? The idea is you take your standard for your crypto, you specify it, and you verify that the implementation meets the standard. So what does the standard look like? Well, this is just one example. If you look at the CHA 20 Poly 1305 standard it's a symmetric cryptographic primitive. This is standardized by the IETF. You'll go look in that standard, you find, there is some various kinds of pseudocode, there's various kinds of test vectors. So using that, I can write a formal specification, and the formal specification could be written in any number of formal languages. This language is called EasyCrypt. That language is called F-star. Some people write it in Coq. Some people write it actually in Python, whatever. You can write a spec for what the algorithm is supposed to do. And any of you could write this, and any of you can read this, really. And then you take your implementation, which might be in C or assembly or Rust or whatever, and you prove that it actually is correct with respect to the formal spec. Also, that it's memory safe. It never reads any memory outside what it's supposed to read. And if you're capable, you will love to prove that it's resistant to certain classes of side channels, right? So if you can analyze the implementation for side channels, correctness, and memory safety, I think that's what we call high assurance crypto. And the good news is that for any algorithm that you care about today, including post-quantum crypto, there is probably an open source implementation with a nice license that you can download and use, which is formally verified. Okay? I'm not saying that it's something I did, it's something Amazon does, it's something Microsoft does, something Google does, and these are all nice open source libraries, including from academia, which you can download and use. Of course, these are all still cutting edge, formally verified, researchy implementations, which means that you might need to put some nice APIs on top of it, but they are very high performance. You don't sacrifice performance, okay? Sometimes these formally verified implementations are even faster than hand-optimized implementations. And you might say, why is that? It's kind of a bit bizarre. Well, there's two reasons. First of all, the formally verified implementations are based on hand-optimized implementation. So you start from an optimized implementation, then you verify it. So obviously, you're not losing any optimizations. But there's also a second, more interesting reason there, which is that there are implementations where at some place in the code, you will see the assembly programmer saying, I think I can skip this particular operation here, but I'm not sure, so I'm going to leave it in because it's safer to leave it in. It's an additional check, additional something. But when you're formally verifying it, you might be able to prove that, hey, you know what, that check or that operation or that set of operations was not needed. I can prove that it's still correct if you remove them. So you can basically optimize your code even further if you had the confidence that was given to you by formal proofs. And that's the reason why many of these implementations, which are formally verified, are actually fast, sometimes faster than the hand-optimized ones that people use. And it's widely used, okay? So it's no longer like a question. It's actually pretty much the default. Later this year, Microsoft and Apple are also going to release formally verified crypto. So everybody, Microsoft, Apple, Google, they're all going to be using formally verified crypto by the end of the year. What we do is we do formally verified crypto in Rust, okay? So here's an example. This is the ML-Chem standard that NIST standardized last year. This is what is used in TLS, in Signal, in PQ3. All these protocols use this standard. And what we do is we write the implementation in Rust. We do a series of transformations to produce from that basically code in a variety of backend provers and try to prove that the code is correct or has some other properties. So in this world, for proving ML-Chem, what we're going to do is prove everything using this verification toolchain called F-star. So we write a spec of ML-Chem by looking at the standard in F-star. We take the Rust code for ML-Chem that Rust engineers wrote, and we run the HAX toolchain to get, again, an F-star model of what that code does. We add some F-star libraries for what Rust is supposed to do, and we throw all of that into F-star to prove that, in fact, it's correct. Okay, and that's, if it's not correct, it basically means there was some kind of panic condition, some correctness bug, some memory bug, and so on. Even if Rust is actually a memory-safe language, there are places where it can crash. So we also want to prove that it will not crash. Once all of this is proven secure, you can either directly use the Rust code, right? You can just directly use it if you're in a Rust application. But of course, many people, especially in embedded systems, don't actually have Rust applications. They want to use C code. So there's also a mode by which whatever this code is gets compiled down to C. And this C code is currently what is used in NSS, in OpenSSH, and so on. So our Rust code compiled to C is what is used in OpenSSH NSS. But Signal directly uses a Rust code. So there are people who use Rust codes, people who use the C code. So what do we mean when we prove things? This is my first kind of proofy or codey slide, so I'm going to go a little bit into it. So this is like a core mathematical function in our crypto implementation, ML-Chem, and it's also in all the other ML-Chem implementations. If you look at any elliptic curve implementation, there is a bigger version of this. And what this function is doing is really taking the input, and I'm going to waffle a bit, it's going to do modulo 3329. It's going to do modulo that prime 3329. So why not just directly do modulo 3329? Well, because the modulus operation actually leaks a side channel because it's kind of optimized differently on different platforms. And so if I directly call the modulus, it will leak a side channel. So instead of doing it directly a modulus, all the implementations typically do only operations that involve multiplication, addition, subtraction, things that are thought to be side channel free. It's not true in all platforms, but let's assume that this is. So this is the operation which is supposed to do modulus, okay? And it's trying to do this in constant time, right? So the first question we ask is, well, is this actually going to crash? Okay, you might feel weird. It's just doing mathematics. Why should it crash? But it can actually, because these operators here, the plus operator, the minus operator, and the multiplication operator, in Rust, those are panicking operations, which means if it overflows or underflows, then in debug mode, this code will just panic. It will just so deep inside your code, you're doing a modulus operator, which is this one. And at some place, you might just overflow the I32 or underflow when you're doing subtraction, and the whole thing will crash, saying, panic, overflow, underflow at runtime. Of course, when you actually compile this for release mode, Rust does the sensible thing, where it actually will not crash, but actually will produce a result which is a wraparound result for you. So is this a sensible thing? I don't know. It doesn't crash, but it produces a wrong result. So it will keep going up to a certain point, and it won't crash, but it will produce a wrong result. So in my world, I prefer to catch this when it crashes because it means I'm doing something wrong, right? So here you want to prove that that plus will not overflow, that minus will not underflow, that multiplication won't overflow. And if you can prove this once and for all, fantastic. Otherwise, you will have to put checks inside that code saying, please check that this is not going to overflow before I do the operation, right? And checks can be very expensive. This is a really kind of performance critical function that is going to be called a lot of times. So to prove that, you basically end up putting preconditions and postconditions. And here the precondition says the input is bounded by this constant. We don't care what the constant is, but the input is between plus Barrett R and minus Barrett R. And if that is the case, I can prove that the output is between plus 3328 and minus 3328. Okay, so that's the spec. And in addition, I'm also adding a correctness spec saying that the result modulo 3329, which is this constant, is equal to the input modulo 3329. So that is the precise functional spec for this function. And once I write that, I can actually prove that the function is actually correct. And if I give this spec and that code to F star and say, please prove that the input, given those input bounds, the output bounds are correct, and this post condition is correct, it'll automatically be able to prove that using an SMT solver. Using other backend provers like Lean or Rock or something, you might have to give a little bit more proof to make it convince it that this is actually correct. Okay? All right, that was correctness. What about side channels? Now, side channels are at the level of source code like C code and Rust code is actually very hard, because you might try to protect against side channels here, but the compiler might reintroduce side channels. Okay? So you really have to trust the compiler that it's not screwing you over if you do something like this. But even so, already at the source code level, whatever language you choose, you can at least do some sanity checks. And the sanity check that we're doing is called secret independence, which means that at the source code level, you should never branch on secrets. You should never access arrays at secret indices. You should never use certain operations that are known to leak side channels. And then beyond that, of course, if the compiler introduces new things, you still want to check that the assembly is not leaking side channels, and that's a different kettle of fish. There are tools that will do that for you. They are not formally so strong, but you can still do a lot of analysis at the assembly level. But this already will eliminate a bunch of bugs for you. So you want to say, in my crypto code, I can do all the arithmetic operations, but not the ones that have different timing depending on what different inputs are, like division and so on. If the inputs are secret, I can't do division on the secrets. I cannot do comparisons over secrets. I cannot branch over secrets. I cannot access an array or a vector at secret index. And this, at the source code level, prevents timing bugs. Okay? And for example, it allows us to find bugs like this one. So last year, when we were first analyzing MLChem implementation in Rust, in our Rust implementation, we found a timing bug where it's similar to the code that we looked at. It was doing some arithmetic blah, blah, blah. And here there was a division. And the division is with a constant. This is also a constant. But the t over here is not a constant. It's a variable. So you go back, you go back, you go back. You see where is t coming from. T is coming from A. You go back, you go back, you go back. And you say, I'm sorry, but this A here could well be a secret because it's related to the message in some way. And so you say, oops, Now I have a secret value, and I'm doing some arithmetic deep inside with that secret value, which is doing a division. And we know that division leaks some information under some compiler modes on some platforms. Not everywhere, but there are sufficient number of cases where division can leak side channel information. So maybe that is actually going to cause us a problem. And indeed, if you really spend a lot of time, and that's what many of our colleagues did, you can actually use that one division right there deep inside MLChem to actually extract the secret key. Okay, and that's the attack that's called Kyber/. There was another variant of it that was called Kyber/2. It was published in CHES last year or this year, got a best paper award and stuff. It was quite nice. Most of the work there actually is actually exploiting this bug, and that's what my colleagues did. Our work was very, very minimal at the beginning, which is to identify this bug that, hey, there is a division. But that was already found just by doing the secret independence check that I showed you in the last slide. So that can actually find you bugs. Of course, after you found all the bugs, it might say there are no bugs left, but you still should be suspicious because the compiler might be doing things that you're not sure of. All right, so summary. So we built an implementation of MLChem and MLDSA. It's in this library called libcrux. It's in Rust. Anybody who uses Rust can use this, but it also gets compiled to C. And in fact, people do use it in C as well. So Firefox, OpenSSH, Signal use this code. What about, that's the crypto code. What about the protocol code? Let's go one level up. Can you still verify it? Yes. What about TLS? Because that's, of course, TLS and its variants are things that everybody needs, whether or not you have custom protocols. At some place, you will be using TLS. So we built this implementation of post-quantum TLS called BERT, and we formally verified it as well. And to do that, we used the same toolchain, hacks. But what we did was for the protocol code, we proved three kinds of proofs. We proved that the code itself is correct, so the message formats, blah, 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 all of these interesting coding things are correct. We proved that the protocol state machine is secure, for which we use ProVerif. And we proved that the key schedule is cryptographically secure, for which we use a tool called SSProof. So we use different tools, but all through the same tool chain for different parts of the protocol. So we have one proof using F star, another proof using SSProof, another proof using ProVerif. And this is something that we published at CCS this year. And the idea there is that, and I think this is actually generalizable to any implementation that is going to do post-quantum TLS or post-quantum whatever protocol that you care of. And what we liked with our methodology is that, first of all, by using the Rust type system, we already eliminated a whole bunch of bugs. So there's no memory safety errors anymore. We enforce state machine correctness. We enforce a bunch of abstraction properties just by using the Rust type system. So that's like baseline. Then for the cryptography, we use libcrux, which is formally verified. Then for all the parsing and the messaging and stuff, which is where a lot of bugs usually are in the message parsing and low-level formats, we use F star to prove that all of those are correct. Then in the handshake, to make sure that it's actually implementing the protocol correctly, we use ProVerif. And finally, for the cryptographic core, which is the key schedule, we use a tool called SSProof. So using all of these, we get more and more and more guarantees, but you can stop wherever you want. I think even if you started and just did it in Rust, you already get a lot of properties. And then the more you do, the more properties you get for the code. So yeah, just some numbers on how much time it takes to verify things and how much code was actually verified. In total, this is about, 3,000 lines of code. So it's not a big implementation. So it's not really indicative of how much time it will take to analyze, a 50,000 line implementation, but it gives you a sense. All right, since I didn't get any interruptions, I'm actually finishing well. So conclusion, there are 3 points I wanted to make. The first thing, and I keep repeating this all over the place, and I think it's kind of obvious, is that the post-quantum transition is about more than just crypto. Just switching the crypto algorithms is kind of the easy part. But in fact, there's a lot more work there because, in fact, often the protocol itself changes and in ways that can actually be broken. So you do need a formal analysis for it. And in constrained environments, the standard crypto doesn't really work exactly the way you want it to. You have to change it in the way you use it, and that needs formal analysis too. And especially since you're going to have pre-quantum and post-quantum protocols in the same ecosystem, you need to be aware of cross-protocol attacks and downgrade attacks. On the crypto library side of things, Right now, fast verified crypto is available for almost all platforms, assembly implementations even for ARM, for Intel and so on. And I think nobody should be using non-verified crypto. So if somebody is selling a non-verified crypto, don't buy it. And the last part, which is about protocol code, since we are all going to be implementing new protocols, if we start by already building informal verification into these new implementations, I think we will save us a lot of pain going forward because we'll be able to maintain those properties as the code evolves. And this is a good opportunity, I think, for us to kind of inject some high assurance into our stacks, and we should not lose it. Anyway, that's my spiel. Questions are welcome.